Hi, it's Chemgal. In this video, we're going to talk about mechanisms. But before we do, I want to talk a little bit about acids and bases. So let's talk about those. You've probably learned that acids like to donate hydrogens, and that bases like to accept hydrogens. This is called the Bronsted-Lowry definition. However, some people like to think that acids accept electron density, while bases donate electron density. Both these definitions tie together, and in a bit we'll do an example to show you how. But now let's look at them from an organic chemistry perspective. The easiest way to identify whether something is an acid or a base is to think about how much electron density it has. So compounds lacking electron density tend to be acids. Whereas compounds with excess electron density tend to be bases. We associate these with special names, so we mostly refer to acids as electrophiles and bases as nucleophiles. Now you might be asking yourself, how can we spot a nucleophile or an electrophile? So remember I said that nucleophiles tend to have high electron density. This means that if a nucleophile has a charge, it's likely to be negative. Some examples of this include hydroxide, NH2, bromide, and chloride. On the other hand, acids tend to be positively charged if they are charged. You can have acids that aren't charged. Some examples include NH4+, ammonium, H3O+, hydronium, HBr, hydrobromic acid, and HCl, hydrochloric acid. A mnemonic that I like to use to remember that nucleophiles have a negative charge is that they both begin with N, so nucleophile, negative charge. Wow, that was a lot of information. Let's look at some examples to tie this all together. Imagine your exam asks you, what might happen if we place hydrochloric acid in the presence of NH2? Draw the mechanism. Whenever I have these questions, I like to ask myself which compound is going to act as the nucleophile and which is going to act as the electrophile. Now it should be easy to recognize that NH2 is a strong base, since we just spoke about it here and how to identify it, and that HCl is actually an acid, and that's going to be an electrophile. So let's go ahead and label them. Here is our electrophile, and here is our nucleophile. I will write it like this for short. I like to think of mechanisms as a fair exchange. So nitrogen is going to say, hey, hydrochloric acid, I really like this hydrogen of yours. I think I want to take it. And in exchange for that hydrogen, I'm going to give you one of my lone pairs. So let's trade. Organic chemists like to show this by drawing an arrow. They draw an arrow going from the lone pair to the hydrogen, and then an arrow showing that the bond is breaking between the hydrogen and the chlorine. You must draw both these arrows to get full points on your test. If you just draw one or the other, your teacher can mark it incomplete and even give you 0 credit. Now for the products. So we saw that chlorine lost its hydrogen. And chlorine initially had 1, 2, 3 lone pairs. So it had initially 1, 2, 3 lone pairs. And nitrogen here gained a hydrogen. So now it has 3 hydrogens. And initially it had 2 lone pairs, 1, 2. But remember, it lost the lone pair to gain that hydrogen. So now it just has 1 lone pair. Now, chlorine gained that lone pair from the nitrogen. So if we wanted to highlight it, nitrogen lost this lone pair and chlorine gained that lone pair. And HCl lost this hydrogen and nitrogen gained that hydrogen. So it was a fair exchange. Now we can begin to understand the definitions that we wrote in the chart. So remember we said that electrophiles tend to act as acids and they donate hydrogen. So we can see that here HCl is donating a hydrogen. Now we can also understand that it's accepting electron density because it accepted that lone pair from NH2. A key point here to remember is that the arrow is showing you the flow of electron density. So we always show the arrow going from the nucleophile to the electrophile. And the arrow shows you the flow of electron density. That's the direction in which the electron density is flowing. So we never ever draw the arrow going from electrophile to nucleophile because that is wrong. So now it makes sense. We also see here that our nucleophile, which is acting as a base, is accepting hydrogens and it's donating that electron density, right? It's donating that lone pair. And you can see it in the direction of the arrow. The direction of the arrow shows you the flow of the electron density, or you can think that it also shows you the direction that the lone pair is going to go in. So whenever you do a mechanism, you always want to reassign the formal charges at the end. So remember we said that formal charge is equal to valence electrons minus surrounding electrons. So let's calculate the formal charge for chlorine. So remember we said that chlorine is a halogen and halogens have 7 valence electrons. And surrounding chlorine right now we have 1, 2, 3, 4, 5, 6, 7, 8 surrounding electrons. And that gives chlorine a formal charge of -1. Therefore, we should draw a negative on chlorine. And now let's calculate it for nitrogen. So nitrogen has 5 valence electrons. And surrounding nitrogen right now, we have 1, 2, 3, 4, 5. 1 from each bond and 2 from the lone pair. So 5 minus 5 is going to be a total of 0. So nitrogen has 0 formal charge. So now we can see here that the charge floated from nitrogen in the beginning to chlorine at the end. So we see that flow of electron density through the negative charge as well. Remember that the negative charge indicates excess electron density, so we saw the flow through the movement of the charge. So now HCl lost that hydrogen in order to become Cl-. It was an acid initially, and then it turned into its conjugate base. So HCl was our acid, and then it turned into our conjugate base. You can think of them like a pair. And NH2 was initially a base, but it gained a hydrogen to form its conjugate acid. It is like a pair. So let's go ahead and draw the mechanism for each of these examples. Remember I told you that the best way to start these off is to identify who's your nucleophile and who's your electrophile. So let's start with example number 1. Would this be our nucleophile or our electrophile? This would technically be our electrophile, and there's a few ways we could have figured that out. We see here that it's an acid, NH4+. It has an abundance of hydrogens that it can donate, and it has that positive charge. So these are key giveaways that this is an acid. You might have been unsure of methanol, and the way that we could have figured out that methanol was a nucleophile was by looking at its functional groups. So we can see here that we have an alcohol group, and if you recall from looking at our chart, this looks similar to hydroxide. We said that hydroxide likes to act as a base. So this guy also likes to act like a base. We can label this a electrophile, and this guy can be our nucleophile. So now how do we draw our arrows? Remember I said that we draw our arrows going from nucleophile to electrophile, always. So we want to draw an arrow from the nucleophilic portion of the nucleophile. So here, remember we said that the action is going to be going on around the oxygen. We can draw in those lone pairs there. And so the oxygen says, hey, ammonium, I'm going to take one of your hydrogens, and in exchange for your hydrogen, I'm going to give you a lone pair. So we can go ahead and draw in that arrow. So we draw an arrow going from the oxygen to the hydrogen, and from the bond between the nitrogen and the hydrogen to the nitrogen. Oh, that arrow looked a little funny. Let me fix that. There we go. So now we showed that the oxygen is going to take the hydrogen. So let's draw what our final products will look like. So now NH4 lost the hydrogen. So now let's draw what our final products will look like. So now NH4 lost the hydrogen. So now it only has 3 hydrogens. And in exchange, so now it only has 3 hydrogens. And methanol actually gained a hydrogen. Where is that extra hydrogen going? It's going to go on the oxygen, right? Because the oxygen gave up one of its lone pairs to the nitrogen. And it was left now with only 1 lone pair. So remember I said that whenever we do these problems, we want to assign the formal charge at the end because the formal charge often moves. We see here that we started with a positive formal charge, so in the end we have to have a positive charge as well somewhere. So we're going to go ahead and calculate it to see where the formal charge is. So remember I said that formal charge is equal to valence electrons minus surrounding electrons. So the formal charge for this nitrogen here, it's going to be valence electrons, which is 5 for nitrogen, and surrounding it right now there are 1 from each bond, and from the lone pair we have 2. So there's a total of 5 surrounding electrons, and 5 minus 5 is going to be 0. Therefore, this nitrogen has a 0 formal charge. What about this oxygen? So let's calculate the formal charge here. So oxygen has 6 valence electrons, and surrounding it right now we have 1, 2, 3, 4, 5. 6 minus 5 makes for a total of positive 1. So we can see that the positive charge actually ended up moving onto the oxygen. So there's always that conservation of charge, right? If you start off with a positive, you're going to end with a positive. It just might be on a different molecule. Let's go ahead and try the next one. So who's our nucleophile and who's our electrophile? And you might be thinking that with water, it's actually hard to tell, right? And why is that? That's because water is called an amphoteric species. So amphoteric species can act as both acids or bases. It just depends on what they're with. If water is with an acid, it's going to act like a base. But if water is with a base, it's going to act like an acid. So we can't look to water to see if it's going to be a nucleophile or an electrophile. We have to look at what it's with. So let's take a look at NaCl. What even is NaCl? So let's take a moment to figure that out. Sodium chloride, NaCl, is actually using an ionic bond. So there's an ionic bond between the sodium and the chlorine here. And if we break this up, we see that what's really going on is that we have sodium plus and chlorine minus. Opposites tend to attract each other. So you can kind of think of it in the sense that sodium is really just hanging out with chlorine, but there's not really a formal covalent bond going on there. So if you wanted to, for the purposes of this video, you can ignore the sodium. And that might make the mechanism easier for you in the beginning, just so that we can continue the mechanism. But later on, you find that you won't have to blot it out anymore. So this is sodium chloride here. And we can draw in its lone pairs. So now you have chloride, and now you can recognize that chloride is actually going to be a nucleophile. Therefore, that's going to make water act as an electrophile. So because water is acting with a base, it's going to act like an acid. So chlorine is going to say, hey, Water. I really like this hydrogen of yours. I think I want to take this hydrogen, and in exchange, I'll give you one of my many lone pairs. And water says sure. So we can draw an arrow from one of its lone pairs to the hydrogen and show another arrow breaking the bond between the oxygen and the hydrogen. So now we formed HCl and we formed OH. So remember we said that chlorine started off with 4 lone pairs, but surrounding it right now, it's going to have 3 lone pairs because it donated one of its lone pairs in exchange for that hydrogen. And what about the oxygen? Oxygen actually started off with 2 lone pairs, but it gained a lone pair from the chlorine, so now it actually has 3 lone pairs. Let's go ahead and reassign the formal charge. So formal charge is equal to valence electrons minus surrounding electrons. So chlorine right now has 7 valence electrons. It always has 7 valence electrons because it's a halogen. But surrounding it right now, it's going to have 1, 2, 3, 4, 5, 6, 7. So 7 minus 7 is going to give us a formal charge of 0. Therefore, chlorine is not charged. And what about this newly formed hydroxide particle? The formal charge of that oxygen, we know that valence electrons are going to be 6 for oxygen always. And surrounding it right now, there's 1, 2, 3, 4, 5, 6, 7. 6 minus 7 gives you a charge of -1. Therefore, there is a negative charge on the oxygen. And that makes sense. You know that hydroxide typically has a negative charge. So you know that you did this mechanism correctly. Now let's take a look at the next example. So you might have recognized this guy, and even if you didn't, that's okay. This is actually called hydrosulfuric acid, or H2SO4. And from its name, you can recognize that it is an acid. I would get familiar with this guy because you're probably going to see him again. So remember we said that acids tend to act as electrophiles. So this guy is going to be our electrophile. And now what's going on here? We see the infamous sodium again. And remember what I said about sodium. So we have NaOH here. But we can imagine that sodium is just hanging out with oxygen, right? There's no formal covalent bond. It's an ionic bond. And basically sodium is positively charged and oxygen is negatively charged. And remember we said that opposites attract. So hydroxide is just going to hang out next to that sodium ion, but there's no formal covalent bond. Remember, it's an ionic bond. So sodium doesn't really participate in the reaction. So if we wanted to, we can blot it out. And that should help give us room to draw in our lone pairs. So this is actually a hydroxide ion. And remember, we said from our list that hydroxide ions are bases. So even if you didn't know that this guy was an acid or an electrophile, you can automatically look at NaOH and recognize that it is a base. So this guy is our nucleophile. So what's going to happen here is hydroxide is going to say, hey, sulfuric acid, I really like your hydrogen. I'm going to take your hydrogen, and in exchange, I'll give you one of my lone pairs. And hydrosulfuric acid says, you know what? Sure. So we could draw an arrow going from one of the lone pairs to this hydrogen, and then another arrow showing that the bond is going to break between the oxygen and hydrogen, and the lone pair is going to go onto the oxygen. And so what do our final products look like? So now hydrosulfuric acid actually lost a hydrogen, and hydroxide actually gained a hydrogen. And now what's going on with the lone pair situation? Well, we started off here with 2 lone pairs, and we actually gained a 3rd lone pair. So now we have 3 lone pairs on this oxygen. And now this hydroxide molecule lost a lone pair to gain that hydrogen. So now we should draw him with only 2 lone pairs because he lost one of them. So now we can go ahead and reassign the formal charge. So the formal charge for that oxygen atom for this oxygen atom, we know that it has 6 valence electrons, and surrounding it right now, there are 1, 2, 3, 4, 5, 6, 7. So 6 minus 7 makes for a total of -1 charge. So now we see that we have a -1 charge on that oxygen. And what about that water molecule we formed? Well, you should already know that water isn't charged, but we can go ahead and calculate it to be safe. So we know that oxygen has 6 valence electrons, and surrounding it right now, there's 1, 2, 3, 4, 5, 6. 6 minus 6 makes for a total of 0. And so we see that water isn't charged, and this confirms that we have the correct amount of lone pairs and we did our problem correctly. Now on to the last example. Who's our nucleophile and who's our electrophile? So right off the bat, you can look at NaNH2 and you can just remember that sodium just likes to hang out next to NH2 because sodium is positively charged and NH2 is negatively charged. So NaNH2 is really just an ionic bond between sodium plus and NH2 minus. Now I want to just show you how we can do it by leaving NH2 alone like this. If we wanted to, we could just draw in NH2's lone pairs. So it actually has 2 lone pairs here. NH2 is going to say, hey, carboxylic acid, I really like your hydrogen. I'm going to trade you one of my lone pairs in exchange for your hydrogen. And so we can draw an arrow going from the lone pair over to the hydrogen, and then an arrow showing that the bond is breaking and the lone pair is going onto that oxygen there. So now what do our final products look like? So we have carboxylic acid turning into actually what's called a carboxylate. So it originally had 2 lone pairs, but what's going to happen is it donates that hydrogen and gains a 3rd lone pair. And now NH2 became NH3, and it lost one of its lone pairs. So now it only has 1 lone pair. And so if we recalculate the formal charge there, we know that the formal charge is going to be equal to, for oxygen, 6 valence electrons minus, surrounding it right now is 1, 2, 3, 4, 5, 6, 7. 6 minus 7 for a total charge of -1. So this oxygen is actually going to be -1, and we call that a carboxylate ion. Don't be so freaked out about these terms. I'm just mentioning them now so you can get used to them. And we can calculate the formal charge for NH3. We know that nitrogen has 5 valence electrons, and surrounding it right now, it has 3 from its 3 hydrogen bonds. So we can just imagine 1, 2, 3, 4, 5. So 5 minus 5 makes for a total charge of 0. And therefore, NH3 has no formal charge. And it looks like we forgot to label our nucleophile and electrophile. So I'll just do that right now. But you should have recognized, right, that NaNH2 is our nucleophile. And a key tip there is when you have sodium in front of something, it's typically going to be in front of something that's negatively charged. And we know that negatively charged things like to be nucleophiles. So that's just a little tip over there. And so therefore, this carboxylic acid is going to be our electrophile. And we know that carboxylic acids are acids, and acids tend to be electrophiles. So that's just some key tips over there. So that's it for this video. If you liked it, please leave a thumbs up and feel free to subscribe. Happy studying!